So maybe just continuing on what he said, I now get what Anindya must have talked about. So I think that must have been some correlation matrix of this type. Maybe if D is your data matrix, you construct a correlation matrix of this type D transpose D, and then look at the eigenvalues, for instance, and calculate the eigenvalue density. That's exactly that Marchenko-Pastur distribution. Whereas if you take a symmetric matrix and construct its eigenvalue density, that's a semicircle law. Okay, so I'll first, I could not get this working in the first talk. So this is what we have already discussed, but now you can see that in pictures. So we saw that there are these outlier eigenvalues of the adjacency matrix or the Laplacian matrix, which are very useful in figuring out maybe the diffusion time scale or anything that's useful. So this is how it will actually look like. If you construct synthetically Erdos-Renyi network and then do the eigenvalues, for instance. So you plot the real part versus the imaginary part, which I tried to draw by hand. This is the actual, this one, it's there in that, taken from this paper. So you see this largest eigenvalue here along the 0 of the imaginary axis. It's a pure real number, and so on. So this is for a scale-free network, and this is for a Erdos-Renyi network. Okay, and so I said that if you had clusters or communities in your network, you will see more and more of such eigenvalues which are away from the bulk. So this is the bulk of the eigenvalues, the cloud, but you see 4 of them here. This has been constructed with 4 communities. Okay. So you see 4 of them here. So this is for again Erdos-Renyi and a scale-free network.
So how do you like construct a like an ER graph with a decided number of
First construct 4 different ER graphs, just put some random very few connections among them. That's one way of doing. Okay, so this is the case where there are 4 clusters but of equal size. So you see that 3 eigenvalues merge to become 1. So this is called degeneracy. So there's one which is a different size from the other 3. Okay. You can do this all yourself if you can write some simple programs. But if you take a real network, like for example, this is from the network of political blogs, so it has directed edges. So you see that it doesn't look anywhere like our ideal distribution that you are expecting. This will always be the kind of difference you will see between the reality and your theories. Okay, nature or even man-made objects need not necessarily obey your nice mathematics. Okay. So you see there are some outliers, but it doesn't look like a circular cloud. So there are theories that tell you what should be the size of circular cloud, but it's not even circular in the first place. So these are facts of real life. And I tried to draw this also, the largest eigenvalue as a function of mean degree. So for one dimensional lattice and ER network, it's actually a straight line, but for a scale-free network, it has a square root behavior. So you can note down, or I leave these slides with Shakti and Chitabra, so you can use the references to look at these things. And finally, I drew the semicircle law. So this is how a real semicircle, real meaning again constructed from a synthetic network. You construct a synthetic Erdos-Renyi network and then calculate this spectral density. So this is how it looks like. This has some peculiarity in terms of this. We'll see that later if we have time. So this is for a scale-free network. So once again, so this is what you expect. Semicircle, but actually what you get is something like this, more like a triangle, and then here near the ends here and here it has a power law decay, which is what is shown here. So which means that it decays a bit slowly. So there are many ways in which things can decay to 0. It can decay exponentially fast. A power law decay is typically a slow decay, compared to exponential decay. Slow and fast has to be in comparison to something. Okay, what you might think as slow might be actually fast to something which is even more slower. Okay. So when I say something like this is slow, it is slow compared to exponential decay. So this is when you like this Watt-Strogatz model. You've been introduced to that, right, at some point. Yeah. So you keep doing rewiring, you will reach from a regular lattice to a random network. So as you keep doing that rewiring, your spectral density actually shows all these changes. Finally, when it becomes a random network, it has this semicircular form. And you also see, for example, this is another this one. So this is spectral density of adjacency matrix. This is for Erdos-Renyi network. So you can see that there is a nice semicircle, but there is also one small peak here. And this is for a Laplacian matrix, which is different from a semicircle. And again, for a scale free, you see approximate triangle and a decay here. Okay, so we'll see this later. Now let's go back to what we were doing. Okay, let me see how much of what I small world transition means there is a critical value of rewiring beyond which it transitions to small world properties. It shows small world properties, the network. Yeah.
Sir, why is there one eigenvalue so far?
So again, these are all peculiarities, which means that there is some correlations or maybe some community embedded in it. Yeah. Okay, so I was telling you about the spectral density by motivating example of, say, harmonic oscillator or
What is exactly happening as we go?
no, here you don't go from here. These are two different things.
What is the right?
This is what is called a normalized normalized Laplacian matrix. You normalize the Laplacian matrix with respect to the degrees. So let's not bother about it right now. Yeah. So these are two independent things. So one, you take a adjacency matrix and do the spectral density. Other is take a Laplacian matrix and okay. The spectral density can be formally written down like this. Okay, so it can be a very threatening piece of mathematics, but all it says is same thing that I said before. Simply count the number of eigenvalues in a given interval. No, that is what it does. So if you know what this delta function is, it simply gives you a infinity every time you hit upon an eigenvalue on the real axis. Okay. So you have a real axis and there are occasional eigenvalues here. So every time you hit upon it, it generates a infinity for you. So you simply count the number of such infinities, and this symbol here says that average over many realizations. So you average this over an ensemble. So if you are going to calculate, let's say, the spectral density of a Erdos-Renyi graph, create maybe 1,000 Erdos-Renyi graph, each time calculate rho of lambda spectral density and average this quantity over them. That's what it means. So it's a usual thing that you do in experiments to avoid at least certain kinds of errors. You say that repeat the experiment many times and take the average. So this is an ensemble of that kind. Okay, so the point that I want to go back to is to say that for the Erdos-Renyi network, you have this semicircular form, and where does this semicircular form comes from. Okay. Maybe I should first define that result for you before before we actually go ahead and do anything else. So, in fact, this rho of lambda will be given by 1 by 2 pi into root of 4 minus x square. X lies between 2 and 2, where x is lambda by n. So, in other words, you take your any of these graphs, calculate all the eigenvalues, scale the eigenvalue by the number of vertices in the graph, divide all the eigenvalues by n. N is a constant, right, for a given graph. You chosen maybe to work with 1000 node Erdos-Renian. Do that, and then compute the that distribution. Rho of x should be x, not lambda. So, it will fall in this form, and this form is exactly the semicircle form. Just try and plot that square root of 4 minus x square, that is semicircular. This is simply some normalization constant. Okay. So, where does this form, where does that analytical result come from? Okay. That is where the random matrix theory comes from. Beyond that, you can see what happens if x is larger than 2. Yeah. So, in any case, for any typical random matrix, actually there is a bound on the eigenvalues. Yeah, you can't have eigenvalues larger than a certain bound. Yeah. Okay. So, now the question is, if I tell you that this this result is coming from random matrix theory, so what is this object, random matrix? Okay. So, in very simple terms, random matrix is a matrix with random entries or random numbers put in here as objects. Okay. So, you can call it some m, and the question that you may want to ask of such an object is, if I have a matrix whose numbers are all random numbers taken from maybe some distribution, just randomly throwing in numbers into the slots, what can I say about its eigenvalues and eigenvectors? That is the main central question in random matrix theory, and the question is very simple or looks simple, but the answers are very hard. Okay. None of that is easily can be easily worked out. The question is, if I have a matrix, in general you can think of it as any n by n matrix, square matrix, and I am putting in numbers randomly from some distribution. You take any distribution you want and you throw in numbers here and fill the matrix. Now the question is, what can I say about the eigenvalues and eigenvectors of such matrix? Okay. So, that is the central question, but the answer is very difficult. I mean, not easy. There are books and books written on trying to answer this question. So, first of all, the way I stated the question is a very broad question, like trying to solve that is almost impossible. But if you restrict yourself to some specific cases, at least you can make some headway. For instance, instead of saying that I will put in fill in it with random numbers the way I want, you can say that I will fill in it with random numbers, but respecting the property that this should be a real symmetric matrix. Okay. So, if I in addition add this additional constraint that it should be a real symmetric matrix, then you can make some headway with that. So, you restrict the class of matrices for which you want to get something out, and this is actually a very broad class of matrices. As you saw in undirected networks, you end up with a real symmetric matrix, and the correlation matrix of this type, that is a real symmetric matrix. Any matrix of this type, D transpose D, is guaranteed to be a real symmetric matrix. So, there is a whole lot of real applications where you end up with matrix which is actually real symmetric. So in quantum mechanics, most of the at least most of the Hermitian systems, they have either real or complex symmetric matrices. So in fact, the reason as to why anyone would think of such a object, why would one worry about, first you create a matrix which has no rhyme or reason, just throwing in random numbers, and then ask the question, what about its sign? Why would one worry about such a scenario in the first place? Nothing in real life is that random that you need to work with these kinds of objects. So one of the original applications of random matrix theory was in nuclear physics in 1950s. So inside the nucleus, interactions were not known. So if you are looking at, say for example, how electron interacts with nucleus, so that is the usual Coulomb force. You can, that's the problem that's solved in all quantum mechanics books. But once you go inside nucleus, look at nucleons for large nucleus like uranium, for large number of nucleons, and all kinds of interactions are present. We don't even know what are those interactions. We don't know all the possible interactions. So in that case, it was Wigner's idea that maybe it can be described by a random matrix. So when you don't know anything about it, you can describe it. Probably it is a complex enough system. There are too many nucleons in the system, and with complex interactions, possibly you can describe it by a matrix which has random numbers. But quantum mechanics also dictates that these matrices are real symmetric matrices. That is where this condition comes from. So he decided that instead of generally looking at random matrix, let me restrict myself to real symmetric matrix. Okay, so that is where this condition comes from. And it turns out that even outside of quantum mechanics, it is very useful condition that you stick to this one rather than generally searching for answers for a more difficult questions. So in RMT, one is worried about the answers for ensemble of matrices. In other words, you imagine that you don't have one, but you have a collection of matrices, and each of them are going to give you, each such matrix is going to give you a set of eigenvalues. Now you average stuff over them, average the eigenvalues over them. Maybe if you are calculating spectral density, average over all of them, or any other quantity that you want to calculate, you average over that ensemble. Okay, now let me give you some flavor of what is the mathematics behind all this, this thing by taking a simple example. I will skip many steps. Let us take a simple example of a 2 by 2 matrix. I will call it H. There are just 4 elements. And since I want to consider only real symmetric matrix, I will, instead of putting H21, I will use H12. So I will assume each of these numbers is a real number, and I have also taken a symmetric matrix. Okay, all right. So this each of these elements is going to be a random number. So it's one realization of a random matrix. Okay, so then you can associate a probability to it. So this is probability of a given matrix, of a given random matrix. Maybe I use some random number generator and created a matrix, for example, something like this, 0.5, maybe 0.32, 0.32, 0.8. Okay, this is a random matrix that I just generated. Okay. So like this you can keep generating more and more, sticking to the condition that it has to be real and symmetric. Now, what is the probability? How many such possibilities are there? Infinite. There are infinite such possibilities, because each of the element can go from minus infinity to plus infinity, and you need 3 independent numbers. The fourth one is just a carbon copy of the other one. So 3 independent numbers are needed for a 2 by 2 matrix, okay. And you can keep on creating any number of such matrices. Now, so this probability says, what is the probability that if you are going to create such matrices, this one will turn up. So that is what this means. Of infinite possibilities, how did I end up with this number? What is the probability that I can actually get this one? So this, you can write it as this probability. Now you write it as a probability that your 1 1 element is this, probability that your 1 2 element is this. You need only 3 of them because the fourth one is the same. So this already assumes that these are uncorrelated random numbers, okay. So putting in some number at h11 doesn't force h12 to be something else, okay. So they are completely uncorrelated, each one does its own thing. Now what we demand is that this probability should remain invariant in the following sense. So you can rotate these matrices by applying a rotation operation, okay. For example, the usual rotation operation would be something like if I do a infinitesimal rotation, a very small rotation, cos epsilon, sin epsilon, right. Now I can apply this to rotate this. So I can do the following: R transpose H R, and this will give me what? Another 2 by 2 matrix, which I will call H prime. So I started with one version of maybe H, and by applying this rotation operator I got another one, okay. Now what I demand is that the probability of getting this matrix should remain the same even if I rotate, okay. That is the crux of the argument. You do whatever you want, you rotate whatever, but the probability should remain the same, should remain invariant, okay. So in other words, you are making the demand that P of H prime should be equal to P of H. So you need to demand this invariance in probability. And if you demand this invariance in probability, actually this is the kind of calculation you can actually do and go through. But I think in the interest of time, if I do this, I won't be able to do anything for. So you can actually calculate R transpose. H is given, R multiply all the 3 matrices, and you can calculate what is H prime. And you can also calculate P of H prime, okay, and so on. If you again, it will take me at least 15 minutes to go through all the matrix multiplications, everything. So if you do that and demand this is the crux of the argument. You demand this, then the fact that you require this invariance of probability will tell you that will tell you the following, that probability of 1 2. So remember that I had put in these 3 probabilities. This is the probability that your matrix element is H11, probability that your matrix element is H12, and so on. Okay. Now this actually fixes your probability to get matrix element H12 to be some constant divided by 2 pi times exponential minus c by 2 H12 square. Okay. So this is where the Gaussianity comes from. You don't put in saying that I will construct a matrix with random numbers coming from Gaussian numbers. You don't do that. You simply demand that I am going to work with real symmetric matrices, but I am going to demand that I have chosen some arbitrary basis to write this number. I'll just rotate and demand that even if I rotate, the probability of getting a given matrix should not change at all. That actually gives you this result. So in fact, it gives you all the three. So you can write down expression for what is the probability of this one. So this will be and similarly
Excuse me, sir.
yeah, one second.
But what is the subscript for P mean?
Yeah, so see, I think even here I should have used a subscript, meaning that all the three need not be the same probability functions.
Okay.
Ideally, I should have used 1, 1, 1, 2 and 2, 2. So here I am differentiating and writing that. That's all. So this gives you that all the three variables H11, H22 and H12 are actually Gaussian distributed. Now you can go back and say I will construct a random matrix where for each of these elements I will draw random numbers from a Gaussian distribution. Yeah, so if you that's what, if you do the math, that is what comes out. I'll tell you what it means. Yeah. PH is simply the product of, okay, let me put in these numbers. Yeah, that will be, so the, no, it won't be different. We have demand that it be invariant. So if you demand that invariance, it tells you that your elements should have a Gaussian, should be random numbers from a Gaussian distribution.
H prime 2 2 is equal to
No. So this is okay. So in fact, this will be equal to, if you want to do the primed one, it will be same because you have explicitly demanded that invariance.
We demanded the product to be same, but you are
No,
specifically saying
not demanding the product to be yeah. So we have demanded the product, okay, P of H to be invariant. Yeah, that's right. Yes.
So you cannot directly write P1 to H1 to equal to P1 to
See, but that is here we have already assumed. 1 minute. We have already assumed that they are product functions. You won't get a probability distribution which depends on two variables. Okay, so what it tells you is that now I will construct this my random matrix, 2 by 2 random matrix, let's say H11. The way I will construct this is I will simply generate random numbers on my computer with random numbers drawn from a Gaussian distribution with mean 0 and the variance that's determined by this 2. So in other words, for all the diagonal elements, these are, okay, these two are diagonal elements, H11 and H22. So it says that the variance is the same for diagonal elements and it's different. In fact, it's half of that for the off diagonal elements. So that's how you will simply construct a real a random matrix which is real symmetric. Simply go and on your computer generate Gaussian distributed random numbers with let's say if you are going to use zero mean and variance 1, here you will actually variance 1 here, you will use variance 2 here. So then put in those numbers here, that will be your Gaussian random matrix. So you would have come across this technical term called GOE. I don't know if it was ever used in your earlier class. An ensemble of matrices that you generate this way is called a Gaussian orthogonal ensemble. So, here Gaussian means that the elements of the random matrices are Gaussian distributed. The term orthogonal means that the probability remains invariant under a orthogonal transformation. So, this is an orthogonal transformation. You take your original matrix, and if you transform your matrix like this R transpose H R, that is an orthogonal transformation. And you know that for real symmetric matrices, if you want to go to a diagonal structure, you need to do an orthogonal transformation. So, that is what it means. Whenever you see a term GOE, it means I have a random matrix with Gaussian distributed random numbers. The probability of obtaining the matrix remains invariant under a orthogonal transformation. So, you construct an ensemble of such matrices, many such matrices, that forms a GOE matrix. And and the Wigner semicircle law actually applies to what are called GOE matrices. Which I had erased here. I had written the Wigner semicircle law for eigenvalue density is exactly derived for the matrices that belong to this class, Gaussian orthogonal ensemble. So, in reality what happens is so in reality what happens is typically often you may not get a perfect semicircle, but you do not see that very well here, but you might have a exponential decay at the tails. So, what is guaranteed is that the bulk of the eigenvalues, which is most of them here in this region, okay, forget this one, but most of them here in this region will follow the semicircle law. And yeah, just one second. And for the scale free network, it's a power law decay here, which is anyway not covered by the semicircle law. Yeah, what's the question?
Do these elements also have to be equal, P1 to H1 to P1 to dash?
Yeah, each one will be equal to, because you basically just demand it.
So just product has to be.
So, okay, strictly speaking, what you have ensured is that the probability of a given matrix is invariant under a orthogonal transformation. So, strictly speaking, P of H will be equal to P of H prime. But because it's a product case, even for individual matrices or for individual elements, it works. Okay, so this is one important, not just the property, but also a metric that you use that originates from random matrix theory. And when you go to real life networks, there you will see huge deviations from the semicircle law. For example, I think I had a figure for this. You must have heard of these terms like assortative and disassortative networks. So, here is the case for assortative to disassortative. So, here until you are in that regime where it is you constructed a assortative network, Erdős-Rényi network, it is still more or less bulk of the eigenvalues do follow the semicircle law. But once it goes to the disassortative regime, which is the ones here, you see that there are huge deviations. Say they won't even look anywhere like a semicircle.
So what characteristics would GOE besides that the decay is exponential?
No, so strictly speaking, GOE does not give you any exponential. It gives a cutoff at +2 and -2. Yeah. So it has that specific formula that doesn't have any exponential, but most real life ones have some exponential behavior. Yeah, and then when you have sparse networks, you do see features like this. when your network is sparse, meaning that you don't have too many edges. You have a large network but very few edges. In such cases, you see this kind of peak in the eigenvalue spectrum, corresponding to the fact that there are many zeros in your eigenvalues. And also there are cases where you can have either another reason for getting that peak is like you can see here. So this is that coefficient which tells you whether it is assortative or disassortative.
So,
It's basically a correlation value, Pearson correlation, yeah, between the likelihood of connection between two edges. Yeah. This one?
What is the P?
What is, okay, so this is actually, so I said that you have to scale your eigenvalue with the size of n. So that is what they have done. So here it's scaled with the lambda by root of n, but they have also added, so p is the probability of rewiring. Okay. So they have taken some additional factor to do the scaling, that's all. So like for example, when it is disassortative, that's another reason why you will get a peak at 0. So these are cases where like in a very ideal case you should expect a semicircle, but then real life is never ideal in all senses of the term. So you will always see deviations of various type, but still semicircle gives you a background. Like if your matrix is truly just made up of random numbers, like the way we constructed a theoretical random matrix without putting in any structures, you should get a semicircle. Yeah, what's your question?
R is correlation between what?
So correlation between our high degree nodes connected preferentially to high degree nodes, or our high degree nodes preferentially connected to low degree nodes. That's the difference between assortative and disassortative.
So this is for for preferential attachment. Right?
Yeah, right. So even for, I mean, the same idea you can use even for ER. Yeah.
But if ER too, it's not.
On an average, it doesn't differ too much because you have a degree distribution is like a Gaussian, but still you have some variance in the degrees. Yeah.
So here R equal to 0 follows the.
Yeah. So R equal to 0 is like completely more ideal ER network. So it follows the semicircle. At the two other edges where it's correlated and anti-correlated, you see deviations. Actually, when it is assortative, it doesn't see too much deviation.
Oh.
Okay. Yeah.
So wherever you are seeing these like distinctive behavior, then the semicircle law, can you just straight away say that the probability conservation is not true over there, like under rotation, those kind of things?
Yeah, that is probably true. See, this is strictly true only when you get a semicircle. When you get anything other than a semicircle, you really can't relate it to an argument like this.
One of the origin might be this.
Yeah, that's right. So in other words, you should think of it in the following way. So I have a very ideal sense of what is randomness in a network, and based on that, my idea of randomness, I've created some formula for spectral density. Now I'm going to compare with real life spectral densities coming from, if they obey, then I say okay, most of it is random because I conceived it as a random network. But if they all deviate like this, then maybe something else is working there, and it means that there is something more than just randomness.
So in an assortative network, is that why we see more clustering, like more clusters, like more outliers?
Yeah, in many cases you will see. Yeah. Okay, so looks like I have about 15 minutes to dismiss the spacing distribution. Okay, so I'm going to skip even more of the calculations now. Okay, so till now we have looked at the spectral density. So you have your like a real line. On the real line you have these eigenvalues placed somewhere arbitrarily, and you calculated in a very crude sense, given an interval, how many are there, and does it change with as you go up in the spectrum and so on. But another quantity which is very useful and quite popular is the spacing distribution. So what I want to emphasize through this incomplete calculation that I tried to show is random matrix theory goes through this kind of hoops. So you, in fact, this is one of those simple cases where for a 2 by 2 matrix you can actually go through every calculation here and get these things, which I didn't do entirely because of lack of time. But the proper random matrix theory actually does this for a n by n matrix where n tends to infinity, and that is a very hard calculation. Okay, so it runs into several chapters in typical random matrix theory books, requires huge amount of applied mathematics. So I will not bore you with it. There is no way one can even start doing that like this. But the interesting thing is that whatever result you get from 2 by 2 actually works, is an excellent approximation for what you get for infinite order matrices. So which is why this working with 2 by 2 is more or less good enough for most of the cases. So the other quantity I want to look at is spacing distribution. So one is just look at positions of these eigenvalues, look at how crowded the spectrum is. The other one is look at the spacing between the eigenvalues and calculate its distribution. Okay. So that you can define a quantity called spacing, which is lambda I plus 1 minus lambda I divided by the average spacing. So, so this is called the spacing, and what you are after is this thing called the distribution, spacing distribution, or eigenvalue spacing distribution. So now once okay, I just erased those three expressions here for the probabilities. So you can start from there and calculate the spacing distribution for the GOE case. Now you understand what is GOE. Now you can continue the calculation from the point where I wrote down those three probabilities, and then complete the spacing distribution. So before I try and even attempt that, let me just tell you what the result is. So this is the spacing distribution. It will look like this, and actually this perfectly works for a ER network. Not surprising, because semicircle law works for ER network. This is just an extension of the same thing. So this also works for ER network, and so this is often referred to as GOE curve or a spacing distribution curve and so on. So once again you can ask the question, where is this analytical form coming from? Okay. So that again comes from random matrix theory. We just need to continue the calculation. So you go back to this matrix here where we started off and calculate its eigenvalues. It's very easy. 2 by 2 matrix. I am sure all of you know how to calculate the eigenvalue of this 2 by 2 matrix. So you will get two eigenvalues, like lambda 1 will be half so this is one eigenvalue. The other eigenvalue will look very similar. Lambda 2 will be, this will be same, there will be a minus sign here and this will be same. So these are the two eigenvalues. Everything will be the same except for this plus will become a minus. And now what you can do is, and in fact their eigenvectors are trivial. the eigenvector corresponding to this eigenvalue will be cos theta minus sin theta, and the eigenvector corresponding to this will be sin theta cos theta. So, if you understand the linear algebra of a 2 by 2 matrix, you will see why it is so. See, this is simply the once I calculate eigenvalues, I have gone from H to a diagonal matrix. So, I have gone to a matrix which will have lambda 1, lambda 2 here. So, in that case, once you go from a dense matrix to a diagonal matrix, the columns of this R are simply the eigenvectors. So, the columns of R, so remove this epsilon and put theta there, they are simply the eigenvectors. That is always true, whether you deal with network or anything, it is a basic linear algebra. Okay. So, you effected a orthogonal transformation from H to a diagonal form, and the columns of R are the exact eigenvectors that you are looking for, and that is what it is.
Is it always diagonal?
Which is?
Is the matrix always diagonal?
No, I mean there is no guarantee that an arbitrary matrix is diagonalizable, but a real symmetric matrix is always diagonalizable. Yeah. Huh? Is there? Oh yeah, sorry. Yeah, there is a square root here, yeah. Okay, so so now you have 3 variables. Your original matrix had 3 numbers, H11, H22 and H12. Either you choose to describe everything that you want in terms of these 3 numbers, or you give up these 3 numbers and trade it for some other 3 numbers, which is lambda 1, lambda 2 and theta. Okay. So, it is a transformation, it is not a simple linear transformation, but you can do this transformation. It is like instead of describing anything that you want in terms of these 3 numbers, you can describe it in terms of these 3 numbers, which means that each of this will be a function of all the 3. Okay. So, you can do that calculation, and whenever you do this, there will be a Jacobian of the transformation that will be involved. I do not know if you get what you want. So, whenever see, because you are going to do a probability transformation, right. So, you are going to transform yourself from P of H to P that will be described by lambda 1, lambda 2 theta. Okay. So, you want the probabilities to be conserved, to be the same. So, the only way you can do that is by adding a constant which will scale the probability, and that constant is called the Jacobian of transformation. So, whenever you do that, you need to multiply by a Jacobian of transformation. So, Jacobian of the transformation is simply a determinant that you need to determine, but I will spare you all the details at this point. I think we are really running out of time. So, here is the methodology. So, I am going to go from describing my probability in terms of this product to a product, replace H11, H22, H12 by lambda 1, lambda 2 theta. Okay. And once you do that, I am going to construct what is the spacing here. So, I have a 2 by 2 matrix which has just 2 eigenvalues. The only spacing possible is lambda 1 minus lambda 2. Okay. Lambda 1 could be smaller or larger, but essentially it is either lambda 1 minus lambda 2 or the other way around, lambda 2 minus lambda 1. That is the only possibility. Okay. If you have large matrix, there are many other spacings possible, but in this case there is only one possible spacing, which is lambda 1 minus lambda 2. You need to do some integrals with delta functions. Okay, I think I'll have to cut down on all that, but maybe finally code the final result for you. If you do everything right, this is the answer that you should get. So this is called the spacing distribution. So actually today we met two distributions. One is the spectral density, which is called the Wigner's semicircle law, and this is called the Wigner's distribution as well. So this is also called Wigner spacing distribution. Both are actually celebrated distributions. Both are very well known, extremely interesting, important, and so on. Both were derived by, at least the semicircle law was actually derived by Wigner, and this one he did not derive this full expression. So he derived it by a very simple argument. Apparently he was giving a seminar somewhere, and finally someone asked him what would that distribution be, the distribution of spacings. See, he quickly calculated and gave a formula then and there, and it took another 20 years for people to actually exactly calculate that. So when they compared the two, it was differing by a factor of pi by 3, which is close to 1. So no one could see the difference. Okay, so that's the reason why it is called a Wigner. So the actual formula itself he did not derive exactly, but he got something which is very close to it. But let's see, before maybe I should okay, so I'll first show you this and tell you what it actually tells us. This is, let's focus on any of these. In fact, all of them are Wigner distributions. It's just a plot of this formula, if you can, for those of you who can't see it. It's just this one. This blue curve that you see here, it's exactly that. And so this histogram comes from the data. Comes from your, you take a large say scale free network, compute the eigenvalues, compute the distribution, and draw the histogram that has a nice agreement with this. It works for Erdos-Renyi graph or a small world graph and so on. And what is plotted here is the corresponding spectral density. So you notice that only for the case of Erdos-Renyi, the spectral density is actually a semicircle. Here it deviates from semicircle, but yet the spacing distribution works quite well. So in some sense the spacing distribution is universal. What it tells you is that it basically says that you can't, it's not easy to get degeneracy. In other words, you can't get two eigenvalues to come close together on a real axis. So let me explain that. So let's say that let's consider a case like I said in the morning, where you have levels which are equispaced. So let's say I put in one level here, then it determines the entire spectrum, because every other one is equally spaced away from that. This is my reference value, everything is equally spaced. So this is an example of a rigid spectrum. You don't have any freedom. Once you place one of them, everything else, the position of everything else is placed. You don't have any freedom. But on the other hand, you can think of another example where I place this, but this does not constrain any other level. Okay. So the next one can come close to it, next one can be far, it can be randomly placed like this. Okay. So this is an example of a spectrum that is free. It's not constrained by anything. So in this case, the spacing distribution will have this form. So in between these two limits, you have something where there is a constraint, that is, I place a level somewhere here, the next one can't be too close, can't be too far. Okay. So, in other words, you have it maintains some social distance, so to speak, between the levels. So, so which is what is the content of this blue line. The probability of getting small spacings is 0. So, you can't have one sitting on top of another, that is impossible. For a GOE matrix, you calculate its eigenvalues, you will not get two eigenvalues sitting on top of one another. It avoids being close to one another, but at the same time it also avoids large gaps. Okay. So, which means that it tries to maintain some correlation among the eigenvalues. So, typically the eigenvalues that come from Erdos-Renyi, scale-free, small world or similar kinds of networks, they do have this property that for very ideal cases, they will the eigenvalues will tend to avoid one another. They will not get close to one another. So, so this property is called level repulsion, and this is all random matrix levels will have the property of level repulsion. Yeah.
What sort of a matrix will give me equal spacing?
Equal spacing, if you probably had something like a one-dimensional network with each node is connected to next k nearest neighbor nodes, they will give you such. For example, any tridiagonal matrix with like for example, if I construct a tridiagonal element and the so everything else here is 0. There are only numbers along the diagonal and along the super and subdiagonal, and it's a real symmetric matrix that will give you something like this. So any version of that, if you increase the number of super diagonals and subdiagonals, you will still get this. So any network with constant k nearest neighbor connections will give you.
What about the other end?
Other end, actually I have not seen I've seen many cases of network giving you this. It's very common in quantum mechanics and all, but I have not seen this. I can't offhand think of a network that will give you this. I don't know if Anindia has something to say on this. Yeah.
Financial correlation networks tend to generate.
Yeah, that is correlation networks do that. So, there are correlation networks which will give you this, but purely a network structure I have not seen. But I guess it's possible to construct, but it will be a very, very artificial one. Okay, so as I close this topic, so what we did was to look at, we defined what is this GOE, what looks like a formidable, dangerous kind of term. We kind of saw what it is, and I wanted to derive, but finally we just wrote down the results and saw what it means actually in practice. So when you see graphs like this, it simply means that the bulk of your spectrum is essentially like as though it is drawn from from simply a random network. It behaves as though it is just a collection of randomness in it. It's only deviations from this that will give you something that's not random. Yeah, in fact, here are some more graphs of similar type. Again, this is for the when you go from regular to a small world network, where you change the probability of rewiring, you still see that generally the spacing distribution is a good approximation to a GOE Wigner distribution. And this GOE is one thing which is useful for networks and even for correlation matrices, but there are other ensembles in random matrix theory. The last count I know at least about a dozen ensembles which have very different characters, very different results, but most of it do not directly apply to network, at least as much as I understand. Okay, we are already exceeded my time by 5 minutes. Can I just take 2 minutes to maybe wind up? And so I thought that I'll say something about the eigenvectors, just as much as, and also I must say that we just looked at two things, the spectral density and spacing distribution, but there are whole lot of other quantities. There's something called a delta 3 statistics, all kinds of long range correlations. So remember that the way you define spacing is the spacing between two nearest eigenvalues. So essentially you are looking at the correlation between the nearest neighboring eigenvalues, but you need not stop with that. You could have actually explored the correlations among eigenvalues which are far off from one another. Okay. So there are random matrix predictions for that, but if you are sufficiently motivated by this, you can go and look up the books. But just as much as we are talking of eigenvalues, we can also talk of the eigenvectors. What does random matrix say about eigenvectors? So the basic idea is the following: if my matrix is basically drawn from random numbers, what can I say about its eigenvectors? And so again I will skip all the math. There is actually only one possibility. If it is actually obtained from a random matrix like this, then your eigenvector components would be simply delocalized, or in other words, so for a 2 by 2 matrix there are only two components. Okay. Your eigenvector could have something like, in fact I wrote down the eigenvector cos theta, sin theta and so on. There can be two components, but if you had a large eigenvector, say n, where n is much larger, then your eigenvector components would be alpha 1, alpha 2 up to alpha n. Now if you try to just plot this quantity, okay, as a function of this index I, so you are plotting, let us say alpha I as a function of I. In this case the alphas are all real numbers, so you do not need to worry. So typically what will happen is, maybe we can even plot the square of the function to avoid the negative numbers. So you will actually get something that will look like this. So this is n, this is 1, something like this. So which means that it equally populates all the nodes. Okay. So whatever you are seeing, whether you are looking at the dynamics or the structural properties, it simply means that there is an equal contribution from all the nodes here. Remember that this 1 to n, this index I runs over all the nodes. So in a purely random matrix, if you had a n by n random matrix like this, which is real, symmetric and all that, this is how it will be. But as we kept talking, the real life is always different from such idealizations. So what you will actually see is, in many cases, you will see things which are which will be like this. Just one possible example. So which means that most of the actually I should have drawn it, so it falls to 0, something like this. So which means that most of the contributions actually come from the nodes which are sitting here. So these kinds of eigenvectors are called localized eigenvectors. Or you say that somehow your network actually shows localization effect, whereas these are called delocalized, which means that they are spread all over the nodes of all the nodes of the network. So this is a typical scenario for RMT case. This is what would happen if it does not follow the RMT. In other words, your conception, your ideal of a random matrix is random numbers thrown in from some distribution, and if that does not fit into the framework of your real data, you may see things like this. It will take various forms, but this is one possible way. Otherwise, This is what the ideal randomness. Yeah. Not summing. This is just plotting each of them. Yeah, each one is each component, square of each component is plotted. Yeah. Yeah, if you sum all of them, it will be 1 actually. Yeah. Yeah, like I said, so one eigenvector would look like this. Okay, you take the square of each of them and plot that as a function of 1 to n. You can plot, you can do that. In a real random matrix, everything will look like this. Yeah, it will be just some fluctuation around some average value.
So then, is there any reason to think that network with a very strong core periphery structure or hub and spoke kind of structure will show the second type of?
Yeah, so if let's say if you have a strong hub and periphery structure and where the connections are not too many between the hub and the periphery, you will see something like this. And these are, you don't need to plot this, you can actually use a quantity called inverse participation ratio, which is actually a sum over this one. This is called the inverse participation ratio, and if the inverse participation ratio is sufficiently small, meaning that it goes to 0, then it's a delocalized one, and if it is a large number, it is a localized vector. So this is how people probe. They don't actually look at it like this. So you have a one number probe of these eigenvectors. I have one figure for that. So here is the inverse participation ratio plotted for some okay, don't ask me what is this gene co-expression network of zebrafish. If you know, you know it, but for me it's just some network. And here is the IPR, the inverse participation ratio. You can see that there are places where the IPR is low, and then there are places where it is sufficiently large. So these are the eigenvectors which are localized, these are which are delocalized. So real life throws up many different challenges. You won't necessarily get a graph like this. It will take all kinds of forms. Each one needs to be analyzed individually.
So by looking at the localized eigenvectors, I can basically say which genes are expressed together.
Yeah, right. Yeah, exactly. Yeah, that's right. Yeah. 4.
So if IPR is tending towards 0, I can assume it's localized.
Yeah, it's delocalized.
Everything is homogeneous.
Yeah, it's populated. Yeah, that's everything contributes. Okay, I think I truncated many parts, but this is the real end of it. So basically, I think I've tried to give you some kind of teaser of what random matrix would involve, like what it means to say something is a Gaussian orthogonal ensemble, what is Gaussian and what is orthogonal and so on. And we tried to derive this kind of demanding certain kinds of invariances. This is how it's done in the usual random matrix literature. 2 by 2 case, if you are interested, try and do it yourself. Relatively easy. If you have to do for the infinite matrix, it's infinitely hard. But if you are interested and working in this field, you should try and go through the books and do it yourself. And I'll stop here. If you have any questions, we'll answer. Yeah.